Let me take you through a few things. The first topic, false positives and false negatives, is a crucial concept in hypothesis testing and decision making. In any system where decisions are made based on data, errors can occur. A false positive happens when a system incorrectly identifies an event that did not actually occur, while a false negative occurs when the system fails to detect an event that did happen. Consider a cybersecurity system that detects malware in a network. If the system falsely flags a legitimate file as malicious, that is a false positive. On the other hand, if it fails to detect an actual virus, that is a false negative. In different situations, minimizing one type of error might be more critical than the other. A medical diagnostic system, for instance, would prioritize minimizing false negatives because failing to detect a disease could have severe consequences. In contrast, an email spam filter might prefer to reduce false positives to ensure that important emails are not mistakenly sent to the spam folder. Understanding the trade-off between these errors is central to hypothesis testing, where we determine the statistical significance of results and choose acceptable error rates depending on the problem's context. Another vital concept is understanding which distribution a dataset follows and how to apply it. In statistical analysis, different probability distributions model various types of data, and recognizing the correct distribution is key to making accurate predictions. For example, a software company analyzing the time between user requests on a server might find that the data follows an exponential distribution, which is common in modeling waiting times. Alternatively, test scores from a large number of students often follow a normal distribution, characterized by its bell-shaped curve. Applying the wrong distribution can lead to incorrect conclusions. In a machine learning context, if an algorithm assumes that data is normally distributed when it is actually skewed, predictions can become highly inaccurate. To determine the right distribution, one might use visualization techniques such as histograms or formal statistical tests like the Kolmogorov-Smirnov test. Once the distribution is identified, appropriate models and calculations can be applied to optimize performance. The final concept we should know is the theory of sampling and how to predict whether people will accept a product or software when it scales up. Before launching software to a global audience, developers often conduct user testing on a small sample of potential users. If this sample is not representative of the larger population, the results may be misleading. Suppose a new application is tested only among university students, but the intended audience includes both young professionals and older users. If the testing group has specific behaviors or preferences that do not reflect the entire market, the software might fail upon full release. This is where statistical sampling techniques such as stratified sampling or random sampling become essential. By ensuring that all key demographics are proportionally represented in the test group, developers can gain a more accurate understanding of how their software will perform at scale. Additionally, concepts like margin of error and confidence intervals help determine how reliable the test results are in predicting broader adoption. Companies like Google and Facebook frequently use A/B testing, a form of statistical sampling, to compare different versions of their products before a full-scale launch. The reliability of data-driven conclusions depends on external validity, which ensures that findings can be applied beyond the sample studied. Contrary to a common misconception, external validity does not merely confirm whether an estimate is biased. It assesses the generalizability of results. This is crucial in observational study designs, where data is collected without direct intervention. In case studies, for instance, researchers focus on a specific subject or scenario, drawing insights without manipulating variables. Such an approach is distinct from experimental designs, where variables are carefully controlled to establish cause and effect relationships. In some studies, data is analyzed at a broader level. Ecological studies exemplify this by treating entire groups as units of analysis rather than individuals. This macro perspective can sometimes lead to ecological fallacy, where conclusions drawn about a group might not hold true for each individual within it. Variables form the backbone of any dataset. Some, like age and height, are numerical, while others, such as gender, are categorical. Among numerical variables, further distinctions exist. Ordinal variables possess a meaningful order, like rankings in a competition, while discrete numeric variables take only whole numbers, such as the count of students in a classroom. Another key statistical concept is probability distribution, which describes how values in a dataset are spread. The normal distribution, or Gaussian distribution, is one of the most important distributions in statistics due to its symmetric bell-shaped curve. This distribution is characterized by two parameters: the mean, which determines the center, and the standard deviation, which defines the spread of data. Many natural and social phenomena follow a normal distribution, making it essential for inferential statistics. The standard normal distribution is a special case where the mean is 0 and the standard deviation is 1. To standardize any given observation from a normal distribution, we use the formula z equals the obs minus the mean all over the standard deviation, which transforms data into a standard normal scale. Hypothesis testing is another cornerstone of statistical analysis, used to make decisions based on sample data. The null hypothesis, H0, represents the assumption that there is no effect or difference, while the alternative hypothesis, H1, suggests otherwise. In hypothesis testing, we assume the null hypothesis is true until evidence suggests otherwise. The decision to reject or fail to reject the null hypothesis depends on the probability of observing the given data under H0. This probability is known as the p-value. If the p-value is sufficiently small, typically below 0.05, we reject H0 in favor of H1. In cases where the population standard deviation is unknown or the sample size is small, the t-distribution is used instead of the normal distribution. The t-distribution resembles the normal distribution but has heavier tails, reflecting greater uncertainty in smaller samples. The confidence interval, a range of values within which the population parameter is likely to fall, is also affected by whether we use the normal or t-distribution. A 95% confidence interval, for instance, suggests that we are 95% confident that the interval contains the true population mean. The central limit theorem, CLT, plays a fundamental role in statistical inference. It states that, regardless of the population's original distribution, the sampling distribution of the sample mean approaches a normal distribution as the sample size increases. This theorem is crucial because it allows us to make predictions about a population based on a sample, provided the sample is sufficiently large and independent. It ensures that hypothesis testing and confidence interval estimation remain valid even when the underlying data is not normally distributed. When estimating a population parameter, such as the mean, statisticians calculate the standard error, which measures the precision of the sample mean as an estimate of the population mean. The standard error is given by the standard deviation divided by the square root of the sample size. Increasing the sample size reduces the standard error, improving the accuracy of the estimate. This principle underscores why larger samples are preferred in research studies. They yield more reliable results by minimizing the margin of error. Bias is another critical issue in statistical analysis. Bias occurs when a sample is not representative of the full population, leading to systematic errors in measurement. A biased sample can produce misleading conclusions, making random sampling techniques essential for reducing bias. By using unbiased sampling methods, statisticians ensure that their results accurately reflect the characteristics of the entire population. Finally, statistical inference relies on the ability to make generalizations from a sample to a population. Information observed in samples is often inferred to apply to larger populations. This process underpins many fields, from medical research to economics, where data-driven decisions are based on statistical modeling. A crucial concept in statistics is standard deviation, which quantifies how much data deviates from the mean. The formula for standard deviation includes N1 in the denominator, a correction for bias, ensuring that sample-based estimates remain accurate. Related to this, variance measures the average squared deviation, offering another perspective on data dispersion. Finally, statistical freedom plays a role in variance calculations. The term degree of freedom refers to the number of values that can vary within a calculation. Understanding this concept ensures proper data interpretation, especially when analyzing distributions like income, which often exhibit positive skewness, meaning a small number of individuals have significantly higher values compared to the majority. When calculating variance for a sample rather than the entire population, we divide by n1 in the denominator instead of n. This adjustment, known as Bessel's correction, ensures that the sample variance remains an unbiased estimator of the true population variance. Without this correction, the variance calculation would systematically underestimate the true variability, leading to inaccurate conclusions. Among measures of central tendency, the mean is the most affected by outliers. This is why robust statistics, such as the median and IQR, are often preferred when extreme values are present. Unlike the standard deviation, which is sensitive to outliers, the IQR remains stable, making it a reliable choice in certain analyses. Alright, I've gone through a lot with you, unlike Just Pray. 11 minutes. Anyway, good luck.
As the clock strikes 12, a quiet plea, Lord, take my heart and set it free from the weight of yesterday's strife. Renew my soul, breathe new life. You've walked before me, you've paved the way. In every shadow, your light will stay. This is my prayer for the